Welcome to this explainer. Today, we're going to unpack the absolute mind-bending scale of our solar system's largest planet, using nothing but the facts. We are heading straight to Jupiter, the undisputed king of the planets. It's a world of total extremes, crushing gravity, and violent storms that, as you'll see, has profoundly shaped our entire cosmic neighborhood. Okay, so let's jump right into the ultimate thought experiment. We are so incredibly used to planets having solid ground beneath our feet, right? But what if there was literally nowhere to land? To answer that question and to figure out what's really going on underneath those iconic swirling clouds, we have to completely rethink our definition of what a planet can even be. Here's our flight plan for today's expedition. We're going to start with the big picture, dive headfirst into that stormy atmosphere, and take a journey all the way to the core. After that, we'll zoom back out to check out its mighty magnetosphere, its own miniature solar system, and finally, the future of exploring the Jovian system. Kicking things off with the big picture, the king of the planets itself. Let's just wrap our heads around the sheer, crushing scale of Jupiter. It is a gas giant so immense that if you treated it like a hollow shell, you could fit more than 1,300 Earths inside it. In fact, it's more than twice as massive as all the other planets in our solar system combined. Now, because its makeup is roughly 90% hydrogen and 10% helium, which is strikingly similar to our sun, by the way, people often wonder if Jupiter is basically a failed star. Well, the truth is, it simply didn't accumulate enough mass to ignite nuclear fusion. If it had grown about 13 times larger, the internal pressure actually would have triggered fusion in its core, but instead it remains the undisputed kingpin of the planets. And that massive size really highlights how Jupiter acted as a sort of cosmic barrier early in our solar system's history. About 4.6 billion years ago, as Jupiter's core grew, its immense gravity essentially cleared a massive gap in the primordial gas and dust disk. This created a pressure bump that trapped swirling dust grains, turning the area just outside its orbit into a highly efficient factory that churned out the very building blocks for the rest of the solar system. Moving into our second segment, let's descend into Jupiter's violent, stormy atmosphere and dive right into the clouds. Because it's a gas giant, there is a complete and total lack of a solid surface. And that frictionless environment, it allows massive, violent storms to rage for centuries, completely undisturbed by any land masses that would normally break them up. Imagine our hypothetical spacecraft plummeting through the upper atmosphere. We'd pass through 3 violently churning chemical cloud layers spanning about 70 kilometers. And you know those vibrant reds, whites, and browns we see from space? Actually, scratch that. They aren't just pretty colors. They're massive plumes of sulfur and phosphorus gases, bubbling up from the warmer interior and chemically reacting in the sunlight. So the crazy part is that without any land to slow them down, these massive anticyclones can last for generations. The most iconic one, of course, is the Great Red Spot. It's a swirling vortex of clouds twice as wide as Earth itself. It generates wind speeds over 300 miles per hour. And incredibly, astronomers have watched the single storm raging for at least 300 years. No way you're seeing that on Earth. Actually, there is a stark contrast between our relatively gentle weather and Jupiter's cowering superstorms. On Earth, moist air rises pretty easily to form storms about 10 kilometers high. But on Jupiter, the atmosphere is incredibly heavy with hydrogen. It takes a massive buildup of thermal energy to trigger convection there, resulting in colossal storms towering over 100 kilometers high. And the lightning? It's up to 10,000 times more powerful than a flash on Earth. And just to make those Jovian storms even more terrifying, data from NASA's Juno spacecraft reveals they produce these bizarre, plunging projectiles called mushballs. Basically, they're charged, slushy hailstones made of a highly toxic mix of water and ammonia, just plummeting through the dark right alongside those incredibly powerful lightning bolts. All right, let's plunge even deeper. We're on a journey to the core now to finally answer our initial question: what actually happens as we attempt to land our spacecraft? Well, the short answer is we wouldn't survive. Long before reaching the center, the crushing pressure and rising temperatures squeeze the gas until it turns into a liquid. Go a bit deeper, and the pressure gets so extreme that electrons are literally squeezed right off the hydrogen atoms. You're left sinking into a churning, electrically conductive ocean of liquid metallic hydrogen. The heat and pressure in this ocean would instantly crush, melt, and completely vaporize our ship. If you miraculously made it to the very center, you'd be sitting in temperatures hitting a scorching 20,000 degrees Celsius. For decades, scientists thought there was this compact, solid rock and ice core down there. But recent Juno data revealed a massive surprise. The core isn't a solid sphere at all. Instead, it's a diffuse, fuzzy, sort of onion-like mix of dissolved heavy elements, spreading across a massive chunk of the planet. Okay, zooming back out into space, let's talk about Jupiter's mighty magnetosphere, its invisible shield. All that spinning liquid metallic hydrogen we just passed through, it acts like a massive dynamo. It generates a magnetic field that is roughly 20,000 times stronger than Earth's. And this magnetic field doesn't look anything like Earth's nice, neat teardrop shape. Instead, it's stretched way out by Jupiter's rapid rotation and extreme centrifugal forces into a massive, wobbly structure called a magnetodisk. Plus, it's constantly being bombarded and loaded with about 1,000 kilograms of sulfur dioxide gas every single second, erupting directly from Jupiter's highly volcanic moon, Io. This extreme plasma-filled magnetic cavity accelerates particles to near light speed, which generates brilliant auroras at the poles. But unlike Earth's auroras, which kind of ebb and flow depending on the solar wind, Jupiter's are permanent. They are fueled internally by the planet's own rotation and the shockingly strong electrical currents connecting Jupiter directly to its moons. Speaking of moons, let's dive into Section 5. Nestled securely within this wildly dangerous magnetic shield is a complex planetary system of its own. It's essentially a miniature solar system currently boasting 95 officially recognized moons. Now, while Galileo Galilei usually gets all the credit for discovering the 4 largest moons back in 1610, it was actually astronomer Simon Marius who gave them the famous names we use today. Taking a suggestion from Johannes Kepler, Marius named them Io, Europa, Ganymede, and Callisto, the mythological lovers of the Roman god Jupiter. And these 4 Galilean moons are wildly diverse. Io is literally the most volcanically active body in the entire solar system. Europa hides a massive subsurface liquid ocean right under its icy crust. Ganymede is the largest moon we know of and is the only one that generates its own magnetic field. And Callisto is this heavily cratered, ancient world. All 4 are locked in a continuous gravitational tug-of-war with Jupiter that heats up their interiors and keeps them geologically alive today. So how do we know all this? That brings us to exploring the Jovian system and the future of exploration. Understanding this intricate miniature solar system definitely hasn't been easy. It's required decades of robotic exploration, navigating those intense radiation belts we talked about, and executing some incredibly daring gravitational slingshots. Every single daring mission to Jupiter has built upon a last. From Pioneer 10 barely surviving the radiation belts in 1973, to the Voyager probes discovering faint rings, to Galileo actually dropping a probe straight into those swirling clouds. Today, Juno continues to map that deep, fuzzy interior, while highly anticipated missions like NASA's Europa Clipper and the ESA's JUICE are currently speeding through space, slated to arrive at those fascinating moons in the early 2030s. So, what should you really take away from all this? Well, it's that Jupiter isn't just some weird anomaly in our own backyard. It serves as our ultimate cosmic laboratory. By studying its extreme weather, its bizarre fuzzy core, and its massive magnetic forces, we are actually learning the blueprint for how giant exoplanets operate throughout the entire galaxy. And I'll leave you with this final, absolutely thrilling thought. As the Europa Clipper and JUICE missions prepare to investigate these distant, watery worlds, we really have to ask ourselves, if the ingredients for life exist right next door, hiding in the dark subsurface oceans of Jupiter's icy moons, are we truly alone in the universe? Because if we eventually discover the origins of life in the deep oceans of these moons, it changes absolutely everything we know about our place in the cosmos.